Hello again everyone, welcome back to this ptet.chemistry channel. So this is a part 2 of the reacting volumes of gases, where in the first video I talk about the complete combustion of a hydrocarbon, how to get the general equation, and how to use the idea of reacting volume of gases as equivalent as the reacting mole ratio of gases, because they are related. They are related by the molar volume of a gas, which is a constant. So we can say the mole of a gas is proportional to the volume of a gas because that is a constant value. So irrespective of what gas you have, when you're talking about gases, the mole ratio of gas is the same as the volume ratio of gas. I also talk in the other video about this general equation of the combustion of hydrocarbon, and I talk about how we can get it by looking at the algebraic expression where you have x, where if this is 1 mole, if this is x number of carbon, you need x there. If this is y number of hydrogen, because of the 2 there, you need to divide this y by 2, because y over 2 times 2 equal to y, number of hydrogen atoms, here and also here. As for the oxygen, you have 2x, so 2x, and the oxygen here is y over 2 times 1 is y over 2. But there is the total number of oxygen atoms. Here you have 2 there, so if this has to equal that, you need to divide this by 2, because when you have that over 2 times 2, that will be equal to the number of the oxygen atoms on the right hand side. So that's why I need to divide it by 2, and then I will get x plus y over 4 here. That's how this general equation of the combustion of hydrocarbon, only hydrocarbon, yeah, compound containing carbon and hydrogen, the complete combustion of it, this is how you can get the general equation. Okay, these are mole ratio. 1 mole reacts with this mole to form this mole and that mole. It's the same as the volume ratio of this is to this is to this, but not this unless this is a gas, because at room temperature and pressure, H2O exists as a liquid water, so typically we do not involve this unless it's specifically stated it is a gas. We can also work it out if we are given the mass ratio. That is what this question is about, and the previous example is asking that as well. The mass ratio, okay? So here, you have an anhydrous calcium chloride that will absorb H2O. So we use anhydrous calcium chloride or anhydrous magnesium chloride when we're trying to do crystallization. We wash something with water, and then we'll have to dry it with a little bit of not crystallization. In organic synthesis, we will do extraction, and then we'll dry it with a little bit of anhydrous calcium chloride or anhydrous magnesium chloride or magnesium sulfate in order to get rid of the last bit of water. Yeah, but that's beside the point here. So what do we know? So you started from C6H12. So the balance equation tells us it's going to be 6 plus 12 over 4, so it's 9O2. I mean, you could balance it from scratch, really. I mean, there will be 6 CO2, there will be 6 H2O, because 12 hydrogen, 6 carbon. So oxygen is 12, plus 6 is 18, so 9 times 2 is 18. There you go, you see it's balanced, yeah? They don't tell you what is what, right? So assuming you have 1 mole, if you have 1 mole, then you will have, so we are talking about reacting mole. Let's talk about reacting mole because we want the mass, okay? So I will use mole ratio here instead of volume ratio, because it seems like we are not talking about volume at all. 6 and 6, all right? So if I have 1 mole of this, it will give me 6 mole and 6 mole of that, all right? So what is the mass then? Therefore, the mass, if I give off 6 mole of CO2, that will be 6 times 44, and there will be 6 times 18, which is the molar mass. So these are the molar mass of CO2. That's the molar mass of H2O. Okay. So this is 1 times the molar mass of C6H12, which is 12 times 6 plus 12. This question is probably simpler than it is, but we have just worked out that 84 gram of this, which is 1 mole, will react with whatever mole of O2, which is not related here because we are just interested in the H2O and the CO2. That's given up by combusting this C6H12, yeah? So 6 times 44, I'll leave it as multiple of 6. And they want the mass of MP over the mass of MQ, okay? So when this absorb water, it will have an increase of 6 times 18, and this will have an increase of 6 times 44. So that is P there, that is Q there. So the increase in mass of P is 6 times 18. The increase in Q is 6 times 44. That's for burning 1 mole of C6H12, yeah? It's all to do with mole ratio, really. The 6 and the 6 cancel, and I hope you can see the reacting mass ratio is whatever water that is given out related to whatever CO2 is given out. 18 by 44, you will get 0.441 if I do that to 2 sig fig. Doesn't matter really. I mean, like, the idea really is mole ratio. Instead of working with volume ratio, we work with mass ratio. Okay, so mass ratios are related by MR. So that's what we do there. And we are told specifically what reacts with what there. So that's the overall reaction there. So moving on. So this next question actually comes from a structured paper. But despite the long question, it was just about what Humphrey Davy and Michael Faraday did back in the early 19th century. So they have a flammable gas, and they say that the flammable gas is a hydrocarbon, so compound containing carbon and hydrogen atoms only, right? So the ideal goal was to determine the molecular formula of A, and they did it via combustion analysis. Okay, so they completely combust it, and then they try to think about the reaction of the product with things like aqueous potassium hydroxide, which you know it as an alkali or a base. It can react with CO2, as you saw from an earlier example. All right, so we need to think about 40 cm³ of the residual gas which remain after cooling. When you react with KOH, you only have 30 cm³ of gas left. So that means 10 cm³ of gas has reacted with KOH. So what is that volume that has reacted with KOH? You can think about it being CO2. All right. The oxygen is almost always in excess because you need excess oxygen to ensure complete combustion of the hydrocarbon. All right. So if I just write down what I know about the general equation, which is that, which you could get as I've shown it twice already, once in the first part of the video and second in the previous question, how I could get the algebraic expression correctly, combustion of hydrocarbon, yeah? Okay, so the volume at start, you started with 10 cm³, so we are back to reacting volume instead of reacting masses, all right? You react with 50 cm³, which is in excess. So it's very important to write down what is what, yeah? So the volume at the end, you have 40 cm³ of gas, but I know I have 0 at the end. Definitely I have 0 at the end. How much do I have? How much do I have? From the following reaction, so 40 cm³ of gas remain, doesn't contain this because this completely combusts. This is not a gas at room temperature and pressure, which means this together, this plus this, will give you 40 cm³. I will still have oxygen because oxygen is in excess, which I forgot to write down O2 there. But 40 cm³ of this, you shaken with potassium hydroxide, which will react and neutralize the CO2 gas, which is acidic. You put in 40 cm³ through KOH, you get 30 cm³ out. So that means 30 cm³ is the gas that doesn't react with KOH, and that is going to be the O2. So the O2 must be 30 cm³. So these are all in cm³, by the way. So I'm working in cm³. So therefore, the CO2 that reacts with KOH must be 40 minus 30, which is 10 cm³. So I don't need to write down a unit because I've written down the unit on the left-hand side. This is water. H2O at room temperature and pressure is just water, not steam at room temperature and pressure. So we are just going to relate the reacting ratio of these, reacting volumes of these gases in order to get the mole ratio as per the equation. Okay, this is what you put in. This is what you have at the end. That is not how much has reacted. This equation shows 1 mole reacts with this mole. This mole is the mole that reacts. It's the things that react, not what you put in necessarily because it's an excess, not what you get at the end because that is unreacted. So we need whatever is reacted, okay? So the volume reacted, that is very important to know that in the equation like this, it is whatever that reacts that give you the product. So all 10 cm cube reacted. If you start with 50 cm cube and you end up with 30 cm cube unreacted, therefore the amount of oxygen that reacts will be 20 cm cube. And the volume formed is going to be 10 cm cube. And then you can compare, oops, I should probably write that further down. So I don't usually draw lines to show to show the division of the things that I label, but I just keep it very neatly so that I know what is going on. Yeah. So the volume ratio is going to be 10 is to 20 is to 10. Simplest ratio, of course you can just simplify straight away if you want to. It's going to be that. And it's important to get this to 1. And why is that? Because if there's no number here, it refers to 1. In order to compare the coefficient, this is the ratio of the volume. Remember, for gas, the reacting volume ratio of a gas is the same as the mole ratio of the gas. This is mole ratio, this is volume ratio. But this is volume ratio also, before I simplify it. 10 is not equal to 1. 1 is the same as 1. Okay, so I have to always make it into 1 in order to compare them relatively. Yeah. So what does it mean then? That means x plus y over 4 is 2. That means x is 1. I can continue my calculation further down, I guess, because I got space down there now. So therefore, y over 4 is 2 minus 1. Y is 1 times 4 is 4. Therefore, A is CH4. That is methane. 1 carbon, 4 hydrogen. Yeah. And the way you can tell your answer is correct is because it's going to be a sensible hydrocarbon. Things like if it's 1 carbon, it must be methane. It cannot be an alkene, right? If you have a carbon but 5 hydrogen, you know that's wrong already. So that means something must be wrong in the calculation. This is in relation to what you know from your GCSE or your O-level organic chemistry, simple organic chemistry. Okay? So moving on to the next question, which there is no next question. So I guess that's it in this video. Quite a short one, but it's meant to be a short tutorial video where I went through problems. So just to recap, what does potassium hydroxide do? What does this equation mean? It's mole ratio of whatever that reacts, not what you put in, not what you get at the end. Well, in here is what you get at the end because this is the volume form. What you form is produced from whatever that reacts. So the reactant here, it's important to work out what is the volume that reacts. Because these are gases, we can compare their reacting volume ratio. They will give us the same as the mole ratio, which we compare to the equation. By making this into 1, that is to divide this by 10 throughout in order to get this to be 1. Only then you can compare the mole ratio with the coefficient in that balance equation, the algebraic balance equation there. Okay, so this is the end of the reacting volume of gases videos. So if you enjoy this video, if you enjoy my channel, spread the words and so that more people can benefit from it. And let me know what else you wish for me to cover, specifically things that are difficult for you or other people to understand. And yeah, so please subscribe to the channel to be notified of future updates. I'll see you in the next video. So thank you very much for watching.